Hi everybody, this is Mr. Lee. In this video, we are going to go over the fundamentals of the velocity graph. Alright, let's begin. So what I want to do initially is to go back to the ramp lab that we did. Okay, it's important to always go back to our paradigm lab because the entire unit is basically based off of those labs. So if you remember from the previous video, I gave you a perfect set of data, and from that data we found that the general math equation gave us x is equal to 3t squared, where k, our constant, was equal to 3 meters per second squared. And if you remember, that constant, it just means what was the value of the slope for the x is equal to t squared graph. K could be any number, and that 3 was just the number that we got from our perfect data set. Okay, and we found that the relationship is x is directly proportional to t squared, and we call this the law of falling bodies, aka the law of objects speeding up, which you might hear me refer to the ramp lab law. All right. And from there, we got a position versus time graph. And our position versus time graph gave us a graph that looked something like this. Okay, now this is how we started off the this unit, but I want us to go back to the buggy lab. Now, if you remember, the buggy lab, we didn't get this graph, right? We got a graph where it looked something like this. Let's go parts of the graph. We got a straight linear line. So my question to you is, how can we connect the buggy lab to the ramp lab? Okay, where is that connection? All right. Now, in order to make that connection, I want you to redraw the position versus time graph, and so will I, but I want you to redraw it with these specifications in mind. I want you to make this curve like almost like a big belly curve. Let me show you what I mean. I'll show you what not to do, and then I'll show you what to do. Okay, we want something like that, where it's like a really big belly, versus something like this, where it's a little bit more flat. We don't want this. All right, so no. Okay, we want something like this. Yes. Now, the reason why I want to do that is because we are going to be drawing over this graph, and we're going to try to see where is the ramp lab in this, where's the buggy lab in this ramp lab. All right, now work with me here. Now, at this point, if you have different color pencils or pens, this will be a perfect time, because I too will be using a different color to really show you what's going on here. Now, if I were to connect my initial point, okay, with my final point, let's say my final point is there, okay, and I were to just draw a line connecting the 2 points, okay, I will get a straight line. Now, what does this line look like? Now, hopefully you're picking up what I'm putting down, and you're thinking to yourself, well, of course, Mr. Lee, that is the line that we got from the buggy lab. And if you said that, you'll be correct. So we can say that this is the buggy lab, right? So we got the linear line. All right. And if you remember from that lab, we had a very important definition that we came across, and that was the definition for the average velocity, which is the change in position over the change in time. Now, that delta t is is going to be our main focus. Okay, so let's write this down. Delta t is for any 2 time points. Right? And if you're wondering, well, what were our 2 time points, Mr. Lee? It was this point right there and that point right there. Okay, so any 2 time points, that was our delta t, and we just connected the line, and we know that that line, okay, that line is the average velocity. You know what? That's so important. We should write this down. So this is the slope equals average velocity. All right. Now, what if we were to truncate or shorten our delta t, make the delta t closer? Okay, if we were to make the delta t's closer like this, and this is the reason why I told you to draw like a big belly. Okay, it helps here. If I were to make these two closer like this and do the same strategy, it will look something like this. All right, so if I were to call this V1, I can call this V2. So what that shows us is the average velocity between those two time intervals. Okay, and let's keep on doing this. What if we were to truncate our delta t even more from here to here? Okay, boom. We can call this V3. All right, now let's define what we are currently making and what we are currently drawing. All right, so we can say the average velocity, we're going to highlight this one later because it's a very important definition, is the slope of secant line. Now, if you remember, this is from your trig class. A secant line, let's define secant line down here, is a line created by connecting 2 points. All right, and we now know that, okay, so for a position versus time graph, secant line is average velocity. All right, so that's very, very important. We are adding to our definition for our physics course. All right. Now, let's go into the minds of Newton and the previous geniuses of our time, these math geniuses. What they were thinking about is, okay, so if I were to shorten our delta t so that they get closer and closer and closer and closer and closer together, is there a point where the delta t is so close that it's basically the same point? And the answer is yes. Okay, so let's write that down. When delta t is basically 0, meaning that your final time and your initial time are the same time. So when t final is equal to your t initial, so let's say like 5 seconds minus 5 seconds, right? So let's put that in parentheses. So 5 seconds minus 5 seconds equals 0 seconds, right? So when our delta t is 0, what do we have? Okay, and what that looks like for us is a single point right there. Okay, so that's our quote unquote our 5 second point. Okay, and we can draw a line for just that point, like so. Boom. Okay, I'm not going to define that yet as V4 because we need to now give this point a definition. When this happens, delta t is equal to 0, okay? This is instantaneous time, okay? Or it's a moment of time. Let's highlight that because that is super important. All right, so that is going to be a moment of time, and we don't call it delta t is equal to 0. How we define instantaneous time is just the letter t. Okay, t is just a single moment in time, and the important idea is this: this is 1 point of time rather than 2. And I'm just going to put delta t in parentheses because that's 2 moments of time. All right, so a lot of very important definitions here. All right, so let's go back to the line that we drew. So we still see the buggy lab, right, in our dotted lines that we're drawing, but now we're taking a look at not a secant line, but when delta t is equal to 0, we call this the tangent line. So let's also write this down. The slope of a tangent line. And right below it, I'm going to define tangent line. So this is when line hits one point without going through the curve. Okay, so tangent line is when it hits just one point and it doesn't go through the curve. This represents, all right, instantaneous velocity. Ta-da! We finally did it. We got to our big word. Okay? So what this means, instantaneous velocity, is how fast we are moving at a moment of time. Perfect. All right, so instantaneous shows us how fast we are moving in a single moment of time. Now, to give you an analogy of what this really means, let's say you're in a car, right? So if you're in a car and this is like your steering wheel, and in front of you, you should have like a speedometer. I'm just gonna draw my speedometer right there. All right, so here we have 0 miles per hour. We're gonna use miles per hour even though we shouldn't in our physics class. And let's say here is 100 miles per hour, and there's usually like a little dial. Okay, and that dial, you know, it can go up or down depending on how fast you're going, right? So we're in a car. Okay, so let's say we were to graph your position versus time, okay, and you're in your car and you have your foot on the gas pedal, so you're constantly going to be speeding up. Whoa! Once again, those are our big buzzwords. We're speeding up. Remember, that's the law of falling bodies, the law of speeding up. That is our ramp lab, all right? So we're speeding up. So if we are speeding up because our feet is on the gas pedal, this is what our graph is going to be looking like. So let's say we travel, so we drive for, let's say 10 seconds, okay? So here, this is the 10-second mark. All right, so you're driving, and if I were to ask you, okay, so let's say I'm sitting right there in the passenger seat next to you, at the 5-second mark, okay, I ask you, according to your speedometer, how fast are you going? How fast are you going? Now, because you're in the driver's seat, and as soon as I ask you, you could just quickly glance down at the speedometer. You could tell me, okay, at the 5-second mark, I'm moving 50 miles per hour, right? And so what that means in terms of this graph is that data point, right? At this 5-second mark, right there, at that 5-second mark, this slope of this line, okay, this slope is equal to, in our example, the 50 miles per hour, okay, at that moment. But you keep on driving, so at the 7-second mark, I ask you, quickly, how fast are you going, right? So here is our 7-second mark. So at that point, I'm going to use a different color so you can see the difference here, okay? At that point, you will quickly glance at the speedometer, right? And then you would say, Mr. Lee, I am going, I don't know, 70 miles per hour. Okay. So you can see that because your feet is on the gas pedal, we are constantly speeding up, and we can actually see this graphically. Now, if you remember from the ramp lab, from the buggy lab, we learned that the steeper your slope, the faster you're going. So if we take a look here at the 50 miles per hour, right, it's not as steep. It's a little bit more flat. So if I were to just draw it, like this would be the 50 miles per hour one. Okay, versus the 70 miles per hour one, which has a steeper slope. It looks a little bit more vertical. That allows us to tell, or that allows us to know that we are in fact going faster at that moment of time. So I just showcased to you a technique that I need you to be able to do. I need for you to be able to draw 2 tangent lines on your curves, okay? And the reason why I am asking you to do this, and the reason why I am requiring you to do this, is because in order for you to verbalize the object is speeding up, I need that proof. And the proof is shown right there, when you draw two different tangent lines, and if your two tangent lines are getting steeper, that means we're speeding up. If your two tangent lines are getting less and less steep, well, that just means we're slowing down. Okay, so the proof is right there in the tangent lines, and I am asking you, I am requiring you to draw two tangent lines. All right, I'm going to do a quick little sidetrack here to show you on Desmos. If you were to type in, let's say, a tangent line calculator, you would get something that looks like this. So in the very first line, I just wrote in our formula. Position is equal to 3t squared. Okay, and I just want to show you how in the beginning, okay, so the dotted purple line right there, that is the tangent line. All right, at the very, very beginning, we can see that our tangent line is not very steep. So this is like the ramp lab. In the very beginning, we weren't moving that fast. But as the object went down the ramp, okay, we can see that the tangent line is getting steeper and steeper, right? So this is pretty flat, this is pretty steep, okay? So what this shows us is here at that moment of time, the object was not moving fast. At this moment of time, because the slope is even steeper, it was moving faster. And by the way, if you're wondering what that blue line in the back represents, that just shows us the 3. Okay, that's the 3. All right. This is easy to find. All I did is I went to Google and I typed in tangent line calculator, and you can try this out yourself. All right. Cool. Let's do a quick little recap. So for the velocity graph, we went with the law of falling bodies, aka the law of objects speeding up, aka the ramp law, and we saw a graph that was parabolic in shape, right? And from there, we tried to put the buggy lab on top of the ramp lab, and we saw that if we just connect the 2 points from there, ta-da, that is the buggy lab. Now, we went to the mind of the geniuses of the past, and we said, okay, what if we shrunk down the delta t, right, the 2 points, and we made them closer and closer together? What happens? Well, what happens is there's going to be a point where you can only make those 2 points as close together as possible, and eventually we're going to get to a point where it's basically the same point, and at that point we call that the tangent point. Right? And that's how we get instantaneous velocity, where previously we only talked about average velocity. All right. Yeah, and the instantaneous velocity shows us how fast we are moving at a very specific moment of time. And I presented to you an analogy of you driving in a car, and at a certain moment of time, if I were to ask you how fast are we moving, you could tell me exactly how fast we're moving. And the very last thing I told you is you need to be able to draw or sketch at least 2 tangent lines. All right. Now, for our class, because we're using this proof of evidence, your tangent line, unless the worksheet specifically asks you for a very specific tangent line, it could be sketch. So for example, if we're whiteboarding, you could just very briefly sketch the tangent lines. It doesn't have to be exact or precise. All right, see you next time. Bye-bye.